This is a video going over the application problems in handout section 1.4. And we talked about how parabolas, one feature of parabolas is they either have a max or min depending on that a value. So if the a value is negative and the parabola opens down, it has a max. And if the a value is positive and opens up, it has a min. And so that's useful for us in some application problems. So in this first problem, we're talking about gas mileage for a new car can be modeled as a function of the car's speed as follows. And I noticed that it's a parabola that opens down because it has that negative a value. And it's asking for the car's best gas mileage. So if we think about, if I were to graph this, mileage will take on a parabolic form. And so what is the best gas mileage or the max? Well, that's going to occur at the vertex. So what this question is really asking is, what is the vertex? So, and the x-coordinate of this vertex is going to stand for the input, which in this case is speed. And the output will be that gas mileage. So when I find the speed for this max, I'm going to do negative b over 2a. I think that's the easiest here. So negative 3 over 2 times negative 1 over 28, which is, well, the negatives are going to cancel. So it's 3 divided by 1/14, or the same thing as 3 times 14. So that's going to be 42. And the units here are miles per hour for the speed. So that's the speed at which the max, the best gas mileage. And now to find what the heck is that best gas mileage, well, I would plug in 42. So I would do m of 42. So again, just plugging that into the original function, plus 3 times 42 minus 31, and that's going to give us 32 miles per gallon. So it's important to look at the equation and see what we're talking about here. And if it's a parabola, then hopefully if we're talking about a max, it's a parabola that opens down. Okay, this one gets a little bit more challenging, and I just kind of want to help you set it up, and then you should see what you can do with the algebra in terms of getting it in a form that you can then find the min. Okay, so we've got a wire that's 40 centimeters long and it's cut into 2 pieces. And each of those 2 pieces is bent into a square. So where should the wire be cut so that the total area of the 2 squares is to be a minimum? Okay, so first let's start with this wire. And we know it's 40, and we're trying to figure out where it should be cut. And so let's just make one, actually, let me erase that, hold on. Let's make one length x, and if it's 40, the other length is 40 minus x. And so some of you probably, which you will be right, you already know what the answer to this is, maybe intuitively from geometry. But but the key here is you got to prove it. So we need to go through this proof. So, and proof means just mathematically show. It's not going to be not like a 2-column proof or anything like that. So each piece is going to be bent into a square. So if this piece x is bent into a square, then at every length, each side length is going to be x over 4, because we want the perimeter of that to be x. Same is true if I do bend the other piece into a square, then each length will be 40 minus x over 4. Okay, so then let's get back to what the problem is saying. It says that the total area of the 2 squares, so if this is area 1 and area 2, we want it to be a minimum. Well, let's first write the sum of the areas in terms of x. So I'm going to say, maybe I'll call it SA, sum of the areas. In terms of x is going to be x over 4 squared. That's the area of the first square, plus 40 minus x over 4 squared. Now, I want you to, I'll start you a little bit, but the idea is to get it into It's going to be a quadratic, and you want to get it into that standard form, ax squared plus bx plus c. And the hope is, since we're looking for a min, we're hoping that a value, if you've done it correctly, should be positive, so it opens up and has a min. So just to make sure we're on the right track here, the mistake some people make is 40 minus x squares. You don't just square 40 and square x. Remember, you got to FOIL it out. So it's going to be plus 1600 minus 80x plus x squared all over 16. And again, from here, you want to make sure it's in ax squared plus bx plus c form. So you want to divide this 16 into each piece of the numerator, and I would just rewrite x squared as 1/16 x squared. Okay, so see what you can do with that. And then once it's in that standard form, negative b over 2a to find that min, and that'll tell you how to cut it. And of course, you can check my solutions. But I want to get to something like 7. 7 is a very typical problem where you're given a piece of information that constrains the problem, and you're going to use that constraint to then write what you're trying to find in terms of one variable. So let's see what I mean here. Okay, so you've got a field attached to the straight bank of a river, is to be fenced, but there's no fencing along the riverbank. Okay, so say we've got this riverbank here, and we're not going to have fencing along the riverbank, but if 180 meters of fencing is available, what is the max area that can be enclosed? Okay, so eventually we're talking about an area equation, but first I've got to work with my constraint. So my constraint is I have 180 meters of fencing. So if I were to let's attach some labels to this rectangle. So x, y, and then we've got x. So 180 meters of fencing, that's standing for the perimeter here. So 2x plus y equals 180. All right, and so that's my constraint. And now I want to work with this equation. The equation that I want to max is area, which is just x times y. Well, we want to find an area in an equation only in terms of one variable. Here's where the constraint comes in. So in order to rewrite area in terms of one variable, we're going to use that relationship between the two variables. So I'm going to say y is 180 minus 2x, and that will allow me to substitute in for y in the area equation, 180 minus 2x. And then I'm working with an area equation only in terms of x. So x times 180 minus 2x, which will give me negative 2x squared plus 180x. And this is perfect because this area equation is a parabola that opens down. So it will have a max. And where is that max area going to occur? Well, at the vertex. So first I'm going to find the x coordinate of the vertex, which stands for the x dimension on this rectangle. So x equals negative b, so negative 180 over 2 times negative 2. So 180 over 4 is going to be 45. So that, and what was our units here? Meters. So the x dimension I've just found is 45 meters. Now to find the y dimension, I'm not plugging it back into the area equation because that will give me the max area. To find the y dimension, I go back to the relationship between x and y. The y dimension then is y equals 180 minus 2 times 45, or 90 meters. So those two are the dimensions of the rectangle, which will maximize the area here. If I wanted to actually find the max area, either I could have plugged 45 back into the area equation, or now that I have both dimensions, I could just multiply them together. All right, so that's a very typical problem in terms of applications for quadratics. Okay, so see what you can do with the next problem, which is similar. It just has a cost element to it. And then you're going to have a problem involving volume in number 9. And then the others are different. They're not these types of applications on this sheet. And then you'll have more practice with this on 1.4b. So see what you can do, and you can also use my solutions as a guide as well if you get stuck.